In this video, we're going to break apart how to find the Thevenin equivalent circuit by first looking at how to find the Thevenin equivalent voltage. In the next video, we'll look at how to find the short circuit current and the Thevenin equivalent resistance. Let's take a look at what the Thevenin equivalent is. If I have a circuit that contains only sources, and these sources may be dependent, or they may be independent. And resistors. Then Thevenin's theorem states that I can replace any such circuit, again it must contain only sources and resistors, with a single source, V Thevenin, in series with a single resistor, R Thevenin. We typically have these two terminals, and we say our load goes here. Usually our load would be a resistor, but it doesn't have to be. It could be any circuit component. Now, let's develop an example, and we'll be using this example for the next video as well. Our example will talk about what exactly it means to replace a circuit with an equivalent one. Presume I have the following circuit. So it meets our criteria. It has a source, and only resistors and that source are in the circuit. Now let us assume that this has two terminals here. This is where my load goes. And for concreteness, let's actually put something in there. Let's put a light bulb in. The circuit symbol for a light bulb is a circle with some curls. Light bulbs, at least the incandescent kind, which is somewhat obsolete now, are measured with a resistance RL. And therefore we could replace it, in theory, with that resistance. Now, let's think of this circuit from the perspective of the light bulb. Just before I connect that light bulb, there's a voltage across those two terminals. If I label them A and B, then just before I connect that light bulb, before all the connections are made, there's a voltage VAB. This is known as my open circuit voltage. It's called the open circuit voltage because it's the voltage across the two terminals when there's nothing there. When there's nothing there, I have an infinite resistance, which is something we call an open circuit. In this example, we can actually compute it, so let's do so. I have these resistors, and in the original circuit, remember before the load is connected, they're in series, which means I can use voltage division. VAB is equal to the series connection of R2 plus R3 over the sum of the resistors multiplied by my source voltage. Notice something important. VAB, the open circuit voltage, does not depend on my load. The voltage across the load may change when the load is connected, but when there is no load there, only the circuit that I care about is contributing to that open circuit voltage, and therefore I can compute it without knowing anything about my load. The first part of Thevenin says VTH equals VAB. Let's see why. We claim that we can replace our complex circuit with the following circuit. When there's nothing connected here, the current flowing through is 0. If this is A and B, then I have a voltage and I can use KCL going this way to see what we end up with. I have VTH minus VR minus VAB is 0. Now VR, we know, is I times R Thevenin. But this is 0. Therefore I have VTH equals to VAB. This was my open circuit voltage. This is my Thevenin voltage. So if I could find the open circuit voltage, then I know the Thevenin voltage. My next step is to find RTH, which we'll talk about in the next video.